right, page 313, section 5.1. Page 313, section 5.1. We are looking at areas under a curve. And we want to figure out how we could find the area underneath the curve of a graph. Like, let's say that we've got this figure that they give us here, y is equal to f of x. If we were asked to find the area between y equals f of x and the x-axis, how would we find the area of this figure? Well, if it was something normal like a triangle or a rectangle or a trapezoid, I have a formula for that. I could do that. Or even if it's something that maybe is a little abnormal, sometimes I can break that into other figures that I already know area formulas for. And so that's how we're going to approach this as well. If I were trying to find the area under this curve, I'm going to go through and I'm going to try and break this up into some type of other figure that I know how to calculate the area of. And today we're going to do that using rectangles. Now, throughout the textbook, there'll be other figures that we use. For instance, you can see right here we've got y is equal to x squared. That's, of course, our parabola. And we're only interested in example number 1 in the piece of it from 0 to 1. You can see we're going to go through and we're going to break that up into 4 rectangles. But later on in the year, we'll go back and we'll break it up using trapezoids. Look at that. Wouldn't that be like a really good fit for that area under the curve if I used a trapezoid? We'll also go back and we'll use parabolas. Because if you think about it, we're trying to use figures that have a straight edge. Even a trapezoid has a straight edge, where this is a curve. And so a parabola might be a little better fit for that because it's a curve. So there are several different ways that we could utilize to approximate the area under the curve. And we're starting today with rectangles. So they suggest to me that, for example number 1, use rectangles to estimate the area under the parabola y equals x squared from 0 to 1, and they start off asking us to use 4 rectangles. So if you're going from 0 to 1, and you're breaking this up into 4 equal pieces, how wide is each of your rectangles? 1/4, right. Now, we actually have a formula for that. It is change in x, and change in x just says take b minus a and divide it by n. In an interval, b is always your stopping point and a is always your starting point. So since they told me to use the interval from 0 to 1, we could have said stopping point minus starting point divided by n, which is the number of rectangles they told me to use. So that would tell me that each of my rectangles would have a width of 1/4. So if I wanted to go through and write those out, I could say, okay, the first rectangle is going to go from 0 to 1/4. And then the second one's going to go from 1/4 to 1/2, and then 1/2 to 3/4, and then 3/4 to 1. These 4 intervals right here are called subintervals because our actual interval goes from 0 to 1. And so these are 4 subintervals within that interval. And that's usually what they're going to tell me is they'll say approximate the area under the curve using 4 subintervals instead of saying use 4 rectangles. And so n will represent the number of subintervals or the number of rectangles that they want me to use. Now, there are 2 different ways that I could calculate the areas of these rectangles. I could use right endpoints or I could use left endpoints. Let's see what they're talking about there. All right. If I go through and I draw rectangles where I'm going through from 0 to 1/4, I'll section that off into 1 rectangle, and then 1/4 to 1/2 another rectangle, 1/2 to 3/4 another one, and 3/4 to 1 another rectangle. The problem is I don't know how high to make that rectangle. And so one way that I could determine the height of the rectangle is I could use the right-hand endpoint of the subinterval to set the height of my rectangle. So on this first subinterval from 0 to 1/4, I could take the right-hand height and use that to set the height of the rectangle. From 1/4 to 1/2, take the right-hand side of that subinterval and that sets the height. Right-hand side sets the height. Right-hand side sets the height. That's what they mean by using right-hand endpoints. The right endpoint of the subinterval will set the height of that rectangle. So to calculate the actual height of that rectangle, I would go through and I would just say base times height. So the base is just going to be my change in x, the 1/4, and the height is going to be this y value. Now, how am I going to find a y value? How do you typically find a y value? Yeah, plug x into the equation. So if right here I want to use the right-hand x value to set the height, then I'm going to take that 1/4 and I'm going to plug it in the place of x in my equation to find my y value. And so that's what you see them doing right here. That's where that 1/4 squared is coming from. That's just base times height, where height is the y value that I get by plugging in the x value into the function, right? So then for the second rectangle, same idea. It would just be base, the change in x, times height, which comes from taking the x value that is the right-hand endpoint of the subinterval and plugging it in to the function. So we're going to plug in that 1/2 into the function. 1/2 squared would give me my y value. And then we continue with that same process. All right? So if I calculate, throw that into my calculator and calculate that, I get an approximation of the area under that curve being about 0.46875. Now, you can see that's not going to be a fantastic approximation, because look at all of this excess that I have like hanging out over. When I calculated the area, I included all of that, and that is not underneath the curve, so it's not actually part of the area under the curve. So that's why they mentioned that this estimate is going to be really high, because I'm going to have included extra that wasn't really underneath my curve. The alternative then would be to set the height of the rectangles using the left-hand endpoint of the subinterval. So in that case, if I went through, again, I'm going to do base times height. My base is going to be 1/4, or the change in x every single time. But this time the height is going to come from the left-hand endpoint of the subinterval. So for this first rectangle on the left-hand side, I would let the left-hand endpoint set that height. For this next rectangle from 1/4 to 1/2, I'd let the left-hand side set the height. From 1/2 to 3/4, left-hand side sets the height. Same thing here, left-hand side sets the height. And you'll notice that when I would go through to calculate this, I'm going to have some extra pieces here that were not included in my area but are actually under the curve. So this is going to be a low estimate, right? Because I'm actually not including all of the area under the curve. So if I'm going to use my left-hand endpoints, when I come down here, again, we've already said that the base is the change in x, but to get the height, again, I'm going to take the x value and plug it into the function to find the y value. And the x value that I'm going to use is the left-hand side of the interval. So on the interval from 0 to 1/4, I would take 0 and plug it into the function. So that's what you see right here, 0 squared. On the next interval, 1/4 to 1/2, I'd take the left-hand side, that x value of 1/4, and I would plug it into the function. So 1/4 squared would give me that y value, that height of that rectangle. So if I go through and I use my calculator to compute that, I'm going to get 0.21875. And so sure enough, you can see there is going to be a value in between those two somewhere. This one's high and this one's low. Going to be a value in between them somewhere. Now, another way that instead of having to draw this whole thing out and reason the whole thing out to figure out what's my left-hand endpoint and what's my right-hand endpoint, if we come back up here to our subintervals, you'll notice that the values that we used for right-hand endpoints over here, we literally just used the right-hand endpoints of each subinterval. We plugged in 1/4, 1/2, 3/4, and 1. 1/4, 1/2, 3/4, and 1. For over here on the left-hand endpoints, we just used the left-hand value in each of the subintervals. 0, 1/4, 1/2, 3/4. 0, 1/4, 1/2, 3/4. So I wouldn't actually have to draw the whole thing out and reason the whole thing out. I could use my subintervals, but we wanted to reason it out the first time just so we can see how those two mesh together and how they're going to yield our formula. So if this is an overestimate and this is an underestimate, the book suggests to me, why not find the mean of the two? Because if you find the mean, the arithmetic average of those two, that might give you an approximation of, kind of somewhere in between. And so we'll do that. If we go through and we add those two values and divide by 2, we get 0.34375. And the actual area under that curve is 1/3, 0.3 repeating. So that's not terrible. I mean, we're only off by 1/100th. Not accurate enough for AP because I have to have 3 decimal place accuracy for them, but that's a decent approximation for that area under the curve for the amount of work that we put into it. Now, a couple of terms that we're going to use here as we're going through, and as we've already mentioned, is going to be the number of subintervals or the number of rectangles that we're working with. A is the starting point and B is the stopping point. But we also want to go through and label these values that we were plugging in down here, like the 1/4, 1/2, 3/4, 1. We want to label those so that we have a way of referencing those to create a formula. And so we're going to say that x sub 0 is our A value, our starting point. So we started at 0, so x sub 0 is going to be 0. And then the next endpoint that we use, you can see it's the right-hand endpoint here and the left-hand endpoint here, but the next value is 1/4. And then the next value is 1/2. So we'll call that x sub 2. And then the next value is 3/4. We'll call that x sub 3. And then the next value is 1. We'll call that x sub 4. So there actually end up being 1, 2, 3, 4, 5 values that we're using for our 4 subintervals. That's why we start labeling with x sub 0. So that by the time we get to x sub n, in this case x sub 4, we will be at our stopping point of B. Okay? So just some terminology there that we're going to utilize. Now, even though we were only off by 1/100th, that's not accurate enough for AP. So do you have any suggestions of how we could make this more accurate? What would we have to do to make this more accurate, more precise? More points, okay? Where are the points coming from? Right, they're coming from the rectangles, right? So by saying that we need more points, we would have to have more rectangles, right? More subintervals. That would be a great place to start. So look there on page 314 in your textbook. They show you the diagrams that we have here where we did left endpoints with 4 subintervals and we did right endpoints with 4 subintervals. We're going to abbreviate that R4 and L4. Okay, so R and L for right and left, and the subscript 4 will tell me the number of subintervals I used. If you go over to page 315, they show you what would happen if we used 8 rectangles instead. What if we did L8 and R8 instead? And if you see those diagrams there on the top of page 315, I don't have nearly as much overhang and underhang. So yes, I'm still going to get overestimates and underestimates, but they're going to be much better. And they actually calculate those out, and if you'll notice, those areas are in between 0.273 and 0.398. So yes, that's a lot more precise than what we were getting here. So the more rectangles I use, the better it's going to be. If you'll notice on the bottom of page 315, they use even more subintervals. And you'll notice that the more rectangles that they draw, the less overhang and underhang you're going to have, and the more precise these are going to be. Flip over to page 316. Look on the bottom of page 316. There's a really good comparison there on the bottom of page 316 where they show you, okay, what if we do right-hand endpoints and we use 10 intervals? Then right beside it if we use 30. Then right beside it if we use 50. We said that this actual area was going to be 1/3. It was going to be 0.3 repeating. And if you'll notice, when you use 10, you have 0.385. When you use 30, you have 0.350. When you have 50, you have 0.343. You're getting closer and closer and closer to that exact value. And you can also see there how the amount of overhang is getting less and less and less. Similarly, on the top of page 317, they go through and they do the same thing with the left hand. They show you left 10, left 30, and left 50, and the exact same pattern emerges. that I'm getting closer and closer and closer to the exact value, and I'm having less and less and less underhang. If you flip back to page 315 for just a second, they summarize those findings in a chart there on page 315. There in the margin, it says let n be 10 or 20 or 30 or 50, which is what we just saw in the drawings. And then they even go beyond that and they say, what if n was 100? What if n was 1,000? What if we actually drew this out with 1,000 rectangles? Then L sub 1,000 would be 0.333. And R sub 1,000 would be 0.3338. We're really, really close there to 3 decimal point accuracy from both directions. Great, so you're telling me that you want me to draw 1,000 rectangles and calculate 1,000 areas 2 times on every problem for the rest of the semester. No. Obviously, there's got to be a better way of doing this. But what they're trying to illustrate to you is the definitions that they give us on page 318. On page 318, from looking at that chart, we could understand how, if I wanted to find the precise area under the curve instead of an approximate area under the curve, if I wanted to find the actual area under the curve, I could do that by using an infinite number of rectangles. As the number of subintervals approaches infinity, my area approximation gets better and better and better and better until, in theory, if I could use an infinite number of rectangles, I would be getting the exact area under the curve, either from the right or from the left. So the way that we could write that is that the area would be equal to 1/3 if I had an infinite number of subintervals or rectangles from either the right or from the left. We've written this one from the right. So here are the formulas that they give us on page 318 for the way that we can calculate the actual area under the curve from either the left or the right. Okay, so let's start with right. From the right, I want to take the limit as n approaches infinity of the right-hand approximation. So that's the limit as n approaches infinity, and let's think about how we got that right-hand approximation. Go back to the example that we did just a moment ago. When we approximated from the right-hand side, look at the values that we used. From the right-hand side, we don't start with x sub 0, right? Because that's the left-hand endpoint. We used x sub 1, x sub 2, x sub 3, and x sub 4. So we started with x sub 1, not x sub 0, and we went all the way to the last value, x sub n. And so that's exactly what my formula says. Start with x sub 1 as the first value that you plug in, and stop when you get to x sub n, the last value that's the same number as, if you're doing x sub 10, if you're doing L10 or R10, then, this would be x sub 10. It would be that same value. Something else that you'll notice is that we have change in x every single time. We could factor that change in x out in front instead of having to multiply by it every single time and just multiply by it at the end. That would be a little bit of a shortcut for us as well. So that's where that formula comes from. Look at the left-hand formula. For the left-hand formula, it says your area would be equal to the limit as the number of subintervals approaches infinity for L sub n. So that would be the limit. Let's see how we could define L sub n by going back and looking at how we did it a second ago. When we did left-hand endpoints, we did start with 0. We used 0, 1/4, 1/2, and 3/4. 0, 1/4, 1/2, 3/4. We did not, however, use that last value. We did not use x sub n. So we would start with x sub 0, and we would stop with the next to the last value, x sub n minus 1. And that's exactly what our formula says. Start by plugging in x sub 0, and stop when you get to x sub n minus 1. So for example number 4 in the homework exercises, they say estimate the area under the graph of f of x is equal to 25 minus x squared from x equals 0 to x equals 5 using 5 approximating rectangles and right endpoints. Sketch it and see if it's an overestimate or an underestimate, and then repeat that same process for left endpoints. Okay, so if we start with our interval, they told me to go from 0 to 5, so that means that a is going to be 0 because it's our starting point, and B is going to be 5 because it's our stopping point, and they told us that we want to have 5 rectangles or 5 subintervals. So how wide is each of them going to be? 1, right. So we could get that with common sense, but we could also use our formula for change in x, because change in x is b minus a divided by n, so that would be 5 over 5, which is 1. So my first interval is going to start at 0 and be 1 unit wide. So we'll go 0 to 1, 1 to 2, 2 to 3, 3 to 4, and 4 to 5. That makes x sub 0, 0, x sub 1 is 1, x sub 2 is 2, x sub 3 is 3, x sub 4 is 4, and x sub 5 is 5. Right? So if we want to do an approximation of the area under the curve, we don't have an infinite number of subintervals. We only have 5. So we can use the formula for calculating the area with the understanding that we're going to get an approximation, not the exact value, because we're using 5 for n instead of infinity for n. All right, so we could go through and say, first off, in the right-hand formula, we're supposed to start by plugging in x sub 1 and stop by plugging in x sub n. So I'm going to start with plugging in x sub 1, which is 1, and then I'm going to plug in 2, 3, 4, 5. I'm going to stop when I get to x sub n, which is x sub 5. So we plugged in 1, 2, 3, 4, and 5. We're also going to need our change in x, and we've already calculated our change in x to be 1. So we can put 1 in the place of change in x. And then what does f of 1 tell us to do? What does f of 1 tell us to do? Plug 1 in the place of x in the function. So if I put 1 in for x in this function, I'm going to have 25 minus 1. I'm going to have 24. If I plug in 2, I'm going to have 25 minus 2 squared. 25 minus 4 is 21. Plug in 3, 25 minus 9 is 16. Plug in 4, 25 minus 16 is 9. Plug in 5, 25 minus 25 is 0. Add those up, multiply it by the change in x, and we get an estimate of 70. And they ask me, is this an overestimate or an underestimate? It's not always going to be the same. If you remember, when we did our original example number 1, the right-hand endpoints gave us a high estimate, an overestimate. That's not always the case. That was an increasing function. This is a decreasing function. So it's going to be different, because if I were to go through, and I don't have to draw this out precisely, just a sketch, but if I were to go through and break this up into my 5 rectangles, and I let the right-hand side set the height of that rectangle, that's going to be an underestimate, right? Look at all the underhang that's not being included in the area. So it won't always be the same. Right will not always be high. I have to just look at it and see what I'm working with. All right, then they asked me to repeat the process with left. So I could go through and say, okay, let's use that formula that we had up here for area using left-hand endpoints. And notice that when we're using left-hand endpoints, we start with x sub 0 and we stop with x sub n minus 1. So we're going to start plugging in 0 and we're going to stop with the next to the last value of 4. So again, plug in 0 and stop with 4. Change in x is still 1, so we can put that in. And again, f of 0 tells me put 0 in the place of x in that function. So that'd be 25 minus 0, or 25. And we've already plugged in and calculated all these other values. So sure enough, we had thought that this would be the underestimate and that this would be the overestimate, and we can see that would be true. And we could go back and find the mean of those two to give us an average of what the approximate area might be. Another way that you can find a more precise approximation for area, rather than using more rectangles or rather than taking the mean of those two, another really practical thing is to use the midpoint of the interval instead of the right end point or the left end point. I mean, go back to that original example that we did in example number 1. If instead of using the left-hand endpoint or the right-hand endpoint, we went to the middle of that interval and let that set the height, look at what a great approximation that's going to give us, because we have a little bit of overhang and a little bit of an underhang, and they kind of cancel each other out. So I need to find the midpoint of each of those intervals. So midpoint, of course, just add them up and divide by 2. So I've gone through and found each of the midpoints for my subintervals. The way then that I would calculate that area is, if you think about it, if I'm trying to find M4, then if I do base times height, the base every time is still going to be my change in x. So instead of multiplying by it every time, I'm going to pull it out in front and just multiply by it once. And then I just need the height. The way that I'm going to find the height for each of those intervals is I'm going to take the x value and plug it into the function to find the y value, right? The x value that I'm using is the midpoint. So I'm going to go through and I'm going to plug in every one of those midpoints. I'm not going to like start with the second one or stop with the next to the last one. I'm going to use every one of those midpoints. And so I'm going to take 1/8 and plug it into the function y equals x squared. So 1/8 squared is going to give me 1/64. 3/8 squared is going to give me 9/64, and so on. And if you'll notice the answer that I get, look how amazing that approximation is. I am only off by 5/1000ths using 4 rectangles. Not 50, not 100, 4 rectangles with midpoints. So the way that we could sum that formula up is we could say that the area for midpoints could be found by having an infinite number of subintervals. And again, the way that we calculate midpoint is we're plugging in the mean or the midpoint of the interval into the function to get the y value and multiplying it by the change in x to have base times height. So we've seen today that to calculate area, we've done it 3 different ways. We've done left endpoint, right endpoint, and midpoint. We could sum that up using this formula. When we say x sub 1 with a star, that star represents you can choose any value you want out of that interval. You could choose the left endpoint, the right endpoint, the midpoint, whatever value you want out of that interval. In so doing, when you use that star, you're saying, okay, here's my height and here's my base. So base times height of the first rectangle, where I'm choosing any x value, left endpoint, right endpoint, midpoint, something else to plug into the function to get my y value, to get my height. So then this would be base times height of the first rectangle plus base times height of the second rectangle plus, and so on until I get the last one. And summing all of those up then would give me my area. And if we had an infinite number of subintervals, then we would get the precise value for area. We could write that even more concisely by using sigma notation. In sigma notation, we can say, okay, let's start with 1, and we can say x sub 1 and go until we get till n, and that would give us, again, that same summation, starting with the first interval going to the last one, of f of x sub 1, sub 2, sub 3, and so on, times the change in x. So we're looking at base times height and the summation to infinity of those. All right, so here is our homework for tonight on page 322. We are going to get a handy-dandy program on our calculator called NumInt. That NumInt program is going to enable us to do what we saw in the textbook today. In our book, the images were showing us there how you could draw out 50 rectangles or 100 rectangles and actually calculate the area from the left endpoint or from the right endpoint. So we're going to get a program that will do that for us as well on our calculator, and we'll be playing around with that in the next part of this lesson. So when you get to 6C, let's hold off on that until we can play around with it on that program.